This is what we use for a calorimeter. It's the soup bowls from like a Chinese restaurant with a cap that fits right on. And then we put a little hole into the top to insert our thermometer. We record the mass of our metal sample and the mass of our calorimeter, and then the mass of our calorimeter with water. Then we record the initial temperature of the water. Let's see if it stays still. We cannot measure the temperature of the metal directly, so we measure it in boiling water and record its temperature. The metal sample is removed and placed into the calorimeter. The cover is put on, and the sample is swirled until the temperature remains constant. After a few minutes, the temperature remains constant at 20.8, and that is T final of the system. Using the final temperature of the system and subtracting the initial temperature of the water, we have 20.8 minus 19 gives us a temperature change of the water in the calorimeter rose 1.8 degrees Celsius. We know the formula for energy is Q equals ms delta T. Using the difference in the mass of our calorimeter minus the mass of the water, we have a mass of 78.53 grams. We know that the specific heat of water is 1 calorie per gram degree Celsius, and we just calculated that it went through a temperature change of 1.8 degrees Celsius. So the water absorbed 141.354 calories. Well, all of the heat came from the metal. So the energy released by the metal is that exact same value, 141.354 calories, but it's negative because it was released. Next, we need to calculate the temperature change of the metal. So we do T final, the 20.8, minus the initial temperature of our metal, which we found to be 97.1, and we find out that the metal went through a temperature change. It cooled off by 76.3 degrees. To calculate the specific heat of the metal, we will use Q equals ms delta T. We know Q is a negative 141.354 calories. We know that the mass of the metal was 19.08 grams. We do not know the specific heat, that's what we're looking for, and we know it went through a temperature change of negative 76.3 degrees Celsius. A negative and a negative will cancel, and the specific heat will be positive. Specific heat always has to be a positive value. So our specific heat comes out to 0.0971 calories per gram degree Celsius. Now we need to compare that to a chart to determine the identity. Knowing that our metal sample was 0.0971, we can look through this list and determine what our sample possibly could be. Could be copper, but that didn't really match color-wise. Could be iron, that's a little high. Could be nickel, that's still a little high. Or it could be zinc with 0.093. Looking at the 4 choices, my bet is that it is, in fact, zinc. So let's find the percent error. Percent error equals the true value minus the experimental value. Take the absolute value of that, divide it by the true. Plugging in our values, the true value of zinc, 0.093, our experimental value, 0.0971, take the absolute value of that, because that'll be negative, divide by 0.093, multiply by 100, we have a 4.4% error. For classroom cooking, chemistry experimenting, I'd say that's pretty good.